Okay, so I'm going to go through some of this wiring methods, ILM, just so we can get an idea of what we're looking at. Section 12 in the code is fairly lengthy, but I personally think it's laid out very well. It's fairly easy to read through because they do break it down into cables and raceways and such. So again, go through the general requirements. Okay, it's going to talk generally about continuity, support, bends. Okay, we can only have certain amounts of bends as far as pulling through our conduit or raceway. Protection, specific requirements. Okay, and then it's just going to get into conduits in general. It's going to start at 12-1000. Okay, and the first thing they're going to talk about is rigid metal conduit. So just to kind of reference the code here. So this is section 12. And we're going to see again general requirements. The first couple pages. Then it gets into conductors. Again, goes into the general portion of conductors. Open wiring. Exposed wiring on exteriors of buildings. Okay, again, this is still very general. Then it starts talking about specifically about flexible cables. Okay, so the use of flexible cord for show windows, portable power cables. Okay, so not just talking about flexible cables. Then it talks about non-metallic sheath cable. Okay, so if you get a question and it gives you the type of wire or multi-cable conductor it is, then just go to that subheading. Okay, these subheadings are obviously in bold here, and go to that. At least that narrows down the search. Okay, then the next one is armored cable, so like AC90, like BX, okay, or Tech. So we got all the rules for that. Then mineral MI cable, aluminum sheath, flat conductor, and then it gets into raceways. Rule 12900. Again, raceways in general first. So it talks about general conductors in raceways, protection of insulated conductors, okay, whether we can pull or whether we have to lay things in. The radii of bends, again, table 7 is going to get us to that too. So this is in general, and then it gets specific, just like the cables did, and starts at 12-1000 with rigid and flexible metal conduit. So that's kind of where the module starts off, is talking about conduit and raceways first. So just to kind of breeze through here too, just in the general section talks about moisture, that we need to follow the requirements of section 22. Okay, so definitely read the general sections too. Don't just rely on going to that subheading and finding the conduit or the raceway that you need. There's some information that's going to be in the general section too. Okay, but then in regards to conduit, we start with rigid flexible metal. Then next talks about rigid PVC conduit. Goes through all the temperature limitations, spacing, support, expansion joints. Talks about EB1, DB2, so also PVC but not rigid PVC. It's different types. DB2 has definitely used that. It's got a thinner wall for direct burial. And we'll go through all the specifics in the module too. Then rigid RC conduit, liquid tight flexible conduit, EMT or electrical mechanical tubing. Then on the next page is electrical non-metallic tubing, surface raceways. Okay, so again, it's breaking this down to the sections: auxiliary gutters, splitters. Okay, again, a huge section, cable tray, but it's laid out really well in my opinion. Okay, it's not too terrible to kind of search and find stuff in here. We'll go through some of the calculations that we're going to do in the module for sure, but read the module, follow along, go to the rules again as it states. If there's an appendix, go check out the appendix. This last section here, 12-3000, is installation of boxes, cabinets, outlets, and terminal fittings. We'll get into this here too. So how big of a box do we need? If I got a certain amount of splices in it, what do I count for conductors in it? How do I size a box for a larger than number 4. Okay, it's got a specific rule for that too. Okay, so the code definitely hits all these things and does, again, I think, a fairly good job in this module anyways of getting you through all the nooks and crannies of the code, and with decent explanation too. Okay, so it's gonna tell you about it, and then it's gonna cite the rules that it's talking about. Okay, so when I normally lecture in face-to-face in this, I kind of go through this stuff just because potentially it depends on what type of the or what aspect of the trade you're in to whether you've seen this stuff or have experience with it. Okay, so I'll just kind of touch generally on some of this stuff, but again, read through it, reference the code when you need, and then I'll definitely hit these calculations. Okay, so first off, again, talking about rigid metal, I'll just mention the tables. Okay, and again, you'll see them if you read them, but talks about our threads. Again, they have to be tapered so that basically when you spin a coupling or a fitting on, it's going to eventually go in and then bottom out. There's something called running threads, and that's when they're not tapered, and you can literally spin a lock nut right all the way through it without it stopping. Okay, so we don't want running threads. It says we have to have at least 3 full threads engaged. Okay, so often we're the one bending, cutting, and threading this pipe, so we have to make sure that we have enough threads and that they're engaged. When they talk about section 18, which is classified areas, so potentially explosion areas, we need 5 full threads on those. Some terminology, again, this would be we talked about this in grounding and bonding, this would be a standard lock nut. Okay, and then we got our insulated metal bushing. Again, this is just how we terminate rigid conduit into a box or into a thin-walled box termination. And then whether or not we're either in wet locations, so we need a weatherproof, so we can get different types of sealing rings or lock nuts that provide that extra protection if we are outside. Then we also have hubs, so if you've worked in the oil field, you probably have seen a Myers hub before. Okay, so we can use those as well too. Just different ways we can terminate it. Again, if you haven't used a lot of rigid, you may not have seen a lot of this. A lot of times we'll go right into a threaded cast box, but that's not always the case. Okay, we do use rigid sometimes when we don't have potentially a big steel rigid fitting or aluminum to go into box. Then it talks about flexible metal conduits. So this is what we would call flex. We got our flex connectors. These are dry connectors. Okay, so there is liquid tight flex. This is not liquid tight. Liquid tight has the PVC jacket over it. Okay, but still, again, if we needed to if it was indoors and we didn't have to worry about the weather, we could use this to go from a junction to a motor or another piece of equipment. They will. It's handy. There are limitations to what we can use and the strapping and all that, so make sure you read that. Then it starts talking about non-metallic conduits, gets into rigid PVC, all the different rules and stipulations for that. Again, we cannot use it if it's going to be 75 degrees or hotter, but we can still pull 90-degree conductors within the conduit. Okay, maximum of 90, so it does say that. Again, our radius of bends we get from table 7. If you're going to do field bends, you should be using an approved piece of heating equipment to do that. Says a bonding conductor for equipment is required in PVC because it is non-conductive. So normally if you have a PVC pipe, you will be pulling a bond through there too, because obviously the conduit is not going to carry our bond for us. We used to field bend with a Tiger torch. It says right in the code not to do that. So you should be using an approved method to bend that. And again, it talks about EB1 and DB2, different uses for that, okay, whether they have to be encased in concrete. Again, make sure you read the differences. The DB2 I've used before was all for undergrounds for townhouse complex. So they ran all the underground feeds in DB2, and then we attached rigid PVC to that DB2, so when we came up out of the ground it was PVC, because you can't have DB2 running out free air. So we do have certain stipulation and rules for using that. Okay, but again, read through it, not too crazy. Talk about the different And to be honest, I have not used all these types of conduits either. Okay, like this rigid RC conduits or reinforced thermosetting resin conduits, I have never used before. But they have their place. Okay, and it just depends on your experience whether you've seen some of this stuff. Okay, again, the liquid tight, very similar to the flexible metal conduit. Just now this has this covering over top to help with the weatherproofing. Here's your liquid tight flex connectors. You get metallic ones or non-metallic. If you've ever had to pull through these 90s, you know it's awful to get through these. It can be done, but it's not the best. Again, there are limitations for how much flex we can run too. Make sure you read through all that. Again, I'm not going to sit here and read the code rules for you and one off. I'll do us all a favor and not do that. But again, this module literally follows the bold subheadings in the code. Okay, it starts with conduit and raceway rather than conductors, but then it gets to the conductors too. So EMT, again, usually in commercial locations, some industrial. Okay, it's thin walled. It usually has a galvanized exterior to help from corrosion. There's different types of fittings. Again, you get steel or zinc die cast. These compression fittings here are used when we are in wet locations, so we call these rain tight couplings and connectors. If you're running your EMT outside and using these connectors, because they are for wet location, you do have to pull a separate bond in there too, and it states that. And I've had to do that in the field. And my thought behind that is these are compression fittings. They don't have set screws. These break really easily, and if they break, come apart, then you've lost your path of continuity as well too. So that's why it's made sense that when I've always had to pull a bond in there, is because these fittings are not. All it takes is one loose fitting, and you've lost your bond, right? Okay, so there are different types of EMT, electric non-metallic tubing. Okay, so this would be like PVC kind of flex, if you will, or they're just calling it ENT, electric non-metallic corrugated thin wall tubing. Yeah, I've definitely used this stuff before in the field as well. It is a PVC material, and it does have some of the same limitations as the PVC. Okay, other raceways. They talk about surface raceways. This would be if you have potentially brick and mortar and you can't fish down, you can run this on the surface. Probably seen this in some applications. Underfloor raceways and cellular floors, read about that. Auxiliary gutters, again, got its own rules about percent fill and all that, again, straight out of the code. Busways, splitters. Okay, splitters when we are basically splitting one line down to potentially smaller load lines. We talked about section 14 about the limitations of that. We'll talk about that in protection and control coming up. Again, different types of wireways. Again, whether you've seen this or not depends on your experience. I'm sure I've seen wireways I worked in Saputo here in Red Deer, and they had a ton of stuff. And wireway, probably not the best location, because after what seemed to be decades, there was something dripping on it and eating away at it. So again, we, as electricians, if we're not always having prints to go off of, we got to make sure we understand what type of environment we're installing this in, and then the limitations of our equipment too. Okay. Wireways, auxiliary gutters. So this is talking about some of the 5C rules apply. That's the multiple conductors in a raceway, so we may have to use that too. Again, they make a distinction between power and control conductors. Okay, so keep an eye out for that. Cable trays, again, you might have some experience with that. Gives you all the separations. This stuff is, again, word for word right out of the code, not too terrible as far as interpretation. I'll give you a shot of that in case you want to check yours. Again, they give you the answer in the back. I try to put the rule beside so that I have an understanding of where I found that answer. So I do try to put the rules in, so you can obviously have a look at that, pause it, check it out, try and see if you can find where those are. If you can't, that's why I wrote the rules there. Cable installation. So now we start getting into the cable part of it. Okay, so we talked about all the different types of conduit, raceways, splitters, gutters, all that kind of stuff. Then the objective 2 gets into cable installations and the different types of cable. So the first one they talk about, non-metallic sheath cable, NMD90 for dry, damp locations are either concealed or exposed. They say it's almost exclusively in residential combustible construction. So residential combustible construction basically is wood studs. Okay, that's where we're going to pull our what we would call Lumex. Okay, but it is NMD90 that we are using. NMW is for category 1 or 2 wet locations, and NMWU, that U is for underground. Okay, so we can actually run that underground. NMW and NMWU have that insulation maximum temperature of 60 degrees as well. Again, you can see this in table 19. NMD90 obviously is for 90. Okay, so watch that if you're doing a calculation where you have to potentially look at temperature terminations. If you're using NMW or NMWU, that's a 60 degree insulation on there. Okay, so that is our Lumex, usually what we, again, like we see if you've done any residential, or even if you've done commercial but they had a wood construction office or something like that, you would pull NMD90 in that as well. Okay, so it starts talking about how we can run this, the supports, how far we should have the holes drilled in our studs, so basically the drywall screws and other cabinet screws aren't hitting our wire. If we can't, we got to put plates over them, over the studs, so that they don't get hit with screws, that kind of stuff. Then it gets into armored cable. Okay, so again, what we would call, or what we called in the trade to me, BX. That's AC90, then ACG90, ACWU90, tech cable. Okay, and it goes through all the difference. It actually does it right here in the module for us, telling us all the different uses and different styles of armored cable we can get. And then talk about the bending radius for them. Again, references the rule that it's talking about. Go look at the rule and read the rule, then read what they say. Again, pretty straightforward, not too terrible. MI and metal sheath cable. Okay, so we talked a lot about this in our conductor section in code earlier. We mentioned RA90 and these different types of cables. So I guess if you didn't know what it is, now you have an opportunity to find out. And then FCC under carpet cable, and little application. Again, I try to, if there is a rule, some of the stuff you find out right in, found this one's right in the module. There's a rule for that, and this is in the module, but also table 19. We'll show you that. Okay, so now I get into some of these calculations. So conductors in a raceway. Basically what we want to do is we want to see if I have a certain amount of conductors, how big of conduit do I need? Or if I have a conduit, how many conductors can I fit into it? There's two ways of doing it. I'll show you the way I do it, and I'll tell you why I do it the way I do it. But you can use table 6 A to K if all the conductors are the same size. Okay, then you can use table 6. If they are of different sizes, you have to go to tables 8, 9, and 10 in order to determine the size. 10 is going to give you the cross-sectional area of the cable. Regardless of the size, you find out all the cross-sectional areas, add them up, and then you're going to go to table 8 to get a percent fill based on how many conductors there are, and then go to table 9 and find the proper size of conduit based on that percentage. Now, things that are important here, we'll get used to these by going in them quite a bit, but 10A is for stranded, 10C is for solid, and B is for photovoltaic cables. And table D is for diesel locomotive cable, so it's a DLO on the table. So if you get a question asking about DLO cable, that's table 10D. Okay? And I do get asked a lot of these questions, and they are right in the module, so make sure you have a read through, because this stuff is, we do have questions like this in our bank too. So there's this example, says, using table 10A, determine the size of the conduit required for the following 600 volt unjacketed stranded conductors pulled into a rigid PVC conduit. So I got 3 number 4s, 2 number 8s, 4 number 12s. Okay, and big thing here is 600 volt unjacketed. Okay, and then RW90XLPE. That's when we go to table 10, we're going to look for all that information, because that's all important for us to make sure we're in the right area. So I'm just going to pull up table 10 here. So table 10A, okay, and again this one is showing us stranded insulated conductors for calculating conduit and tubing fill. So that question says we got 3 number 4s, and we're looking for RW90 XLPE. So there's RW90 XLPE, RW90 XLPE, RW90, right there, RW90 XLPE. Okay, so there's various columns. We got to pick the right one. One is 600 volt, or 2 of them are 600, one's 1,000. So we have to narrow it down. Ours is 600. So now we're down to these 2. Now it says unjacketed. So what you want to do is check these little, this one is a cross, this is a little asterisk. If we flip over, there's notes right there that'll tell you the one with the asterisk is unjacketed, the one with the cross is jacketed right here, and the one with the double plus signs includes apparently EPCV, whatever that is. Don't worry about it too much, because I don't. So we're in the 600 volt, and we're looking for, in this question, unjacketed. So we're looking for the one with the asterisk. So that's this column right here. Okay, so there's the asterisk telling me that 600 volt RW90 XLPE. So now when I look for these conductors, I'm looking for the area in the millimeter squared to see how much they're going to take up inside that conduit. So I have 3 number 4s. So I'm looking at number 4, go over to the area, and I get 52.46. Okay, so that's what they got here. 52.46, and they're timesing it by 3 because there's 3 of them. The number 8s should go across here. They're 28.17. So that's right there. And again, there's 2 of them. And then the number 12s are 16.65. So we will go and look here. Sorry, I'm looking at number 12. Did I look at the wrong spot? Oh, I did, sorry, 11.61. See how easy that is? 11.61, there's 4 of them. And then we total them all up. Then we go to table 8. And that's going to give us our percent fill. So we go to table 8, and it's based on conductors or multi-conductors. Okay, not lead sheath, not in this case. Not in many cases either. You're mainly going to be up in this here. So we're looking number of conductors or cables. Well, we had 9 in there, so we're definitely over 4. So we're in that 40% maximum fill. So then when we go to table 9, this is listed by the different types of conduit. So rigid metal, flexible metal. This table 9C is rigid PVC, EB1, DB2, rigid RTRC. Okay, so they all have their subheading. There's a lot of them. Liquid tight flex, non-metallic liquid tight, EMT, ENMT. Okay, there's obviously several. Make sure you're in the right table. So this one specifically said we need to know what size of rigid PVC. So I'm going to go to table 9C, and table 8 told me to go to the 40% column. And what I'm going to do is I'm going to look for that across that total area that I found here. So this 260.16, I'm going to go down to 40% until I see a conduit that can satisfy the 260. Looks like I'm going to have to go up to a 317, which is a 35 mil conduit. Okay, so that's how I would find out what size I would need of rigid PVC. So you do the calculations, find the area millimeter squared, and then just come over and find the conduit size. So that's what they've done here, and say that it's a 35 mil PVC, rigid PVC conduit. Okay, so that's how we do that, and they're pretty standard. They're not too terrible once they go through that. Again, if we have different sizes, so that was in that question, we had number 4, number 8, number 12. We have to get to the millimeter squared or the cross-sectional area of that, so we're going to go to table 10 to find that. Then we go to table 8 to find the percent fill. Then we go to table 9 to actually find the conduit that we need, the size. Parallel conductors, again, we just want to have an understanding that if we have 2 runs, we're going to split the ampacity in 2 before we size these. Obviously, if we're splitting them up in parallel runs, we're going to reduce the size of our conduit as well. So to go through an example on that, again, they're dividing it by 2 here because we got parallel runs. Just be cautious of the fact that if you are splitting runs up and say they are in liquid tight flex, one of the things about liquid tight flex is that it has to have a bond going through it, so you'd have to size that bond first too, and then also add that into the equation, okay, because it's still taking up space in there. It might not tell you that it needs a bond. You're supposed to know that after you read through the limitations of liquid tight flex. Okay, so watch out for stuff like that. Goes through and finishes the example. This is the note that makes me use table 8, 9, and 10 all the time. It says 6A to K will not always give the same results for a single size of a conductor as 8, 9, and 10. If the minimum trade size conduit or tubing is required, it is recommended to use tables 8, 9, and 10, as table 6 are sized to the smallest internal diameter of of tables 9A through J, and may result in a larger trade size of tubing or conduit. So if a question on a TQ or an IP says, hey, we need the minimum, then definitely you're using 8, 9, and 10. Okay? So if that's the case, I'm not usually going to use table 6. I'm going to use 8, 9, and 10. Unless the question specifically goes out of its way to say the conductors are all the same, I might do it and then double check even. But for the most part, I stick to 8, 9, and 10 just so I don't get myself in trouble. So these objective 3 exercises, I got these broke down too, just so again you can find the answer. So this one I did go to table 6 because it says there's 4 of them. They're 4 number 3/0 T90. So I went right to table 6K and I found out what I needed to do for that. 2 and 3 are going to get us into areas of not the same conductors. So the first one, I would say that it's got flexible metal conduit required for 3 number 4 power conductors, 3 number 12 control, and 1 number 8 bonding. All have RW90 XLPE 600 volt unjacketed insulation, so that's going to tell me what column to go to in the table 10A. So again, I'll put this on here. By all means, make sure you can go and find these. So I got my 3 number 4s. I went and found their area from table 10. Went and found the area of the number 12s and the area of the 8s. Then I multiplied the amount of conductors that I have in there, got a total. That's what they were looking for. Question 3, thing we got to watch out for here is they're saying that we're splitting this into 3 parallel runs. So I took that original ampacity, divided by 3 to get this new parallel run ampacity, sized my conductor from table 2 in the 75 degree, because that's what it said up here. So I see I need 3 runs of 3/0 that are good for 200 amps. Gave me the type of conductor I needed. So I know now I'm just sizing it per conductor, even though there's going to be 3 runs, they're all going to be the same. So I get 3 3/0. I go to table 10, get 201 as the millimeter squared, times that by 3, I get 603. Now the last thing we got to do is not forget that these are run in flexible metal conduit to the motor. And we often do have a run of flex to a motor or a piece of machinery that potentially vibrates or moves, because we don't want a rigid connection there. So if we do have flex, then we need to have a bond. Okay, so they didn't tell us there was a bond again, but we need to know that. So the bond, because it's flex, I go to table 16. Off of that table, I find I need a number 6 going off of the 200 amp. I think I went off the wire, the conductor size there. It's a little bit different with parallel runs. You wouldn't want to use the overcurrent because then it would get, you'd have an extremely large bond. So I think I just went off the 200 amps. I used a number 6. Went to Table 10 for number 6 got its cross-sectional area. And then we'll go and add that to the 603 from the 3/0, and that's how we get the total. Okay, so be careful about that. Make sure that you have an understanding that if it's whatever type of conduit, even if it was PVC, we got to have a bond in there. Okay, so they're going to test you on that and not give you every little piece of information. Okay, so I'm going to stop it there because it's been a half an hour here. I'll stop there and then I'll try and make another video for the last objectives, and we'll go from there.